Okay, we're back. We've proved a theorem that gives us a pairing, that gives us an embedding of ek mod m ek into some group of Homs that has finite domain and finite image. So now we're going to try to put it all together into a very concrete example. So for concreteness, let's take m to be 2, and we are going to assume, like before, that the M torsion is defined over K. So I'm going to assume that our elliptic curve has full 2 torsion defined over K. That is a mild assumption because, well, that can happen over Q. Not for every elliptic curve, but that happens for many elliptic curves over Q. Or I can take my elliptic curve over Q and go up to a number field where all the 2 torsion is defined over that number field. That's at most an S3 extension, the extension of degree 6 of Q. So you can work there if you want, and then it applies to all elliptic curves. All right, so the elliptic curve has full 2 torsion. If it's in short-Weierstrass stress equation, what that means is that is y squared equals f of x, and the f of x factors completely. X minus E1, x minus E2, x minus E3 for some EI in K, and the EIs have to be different because it's an elliptic curve, it's smooth. If there was a coincidence, it would not be as smooth. Let's call the points of torsion TIs. TI is EI, 0. Okay, these are the non-trivial torsion points. Okay. Now, what do we need? To compute the pairing, we need these FT functions that come from the Weil pairing. So how about we put FT I of xy to be the function x minus EI, because we computed that long ago in video, I don't know, 3, 4 of the whole series. We proved that the divisor of these functions are precisely 2ti minus 2o, which is by definition what the function has to be for the Weil pairing. So this is great. It's the simplest. It's really simple. The definition of the FTs is very simple. We need the g function. The g function, well, we can compute FTI composed with multiplication by 2, that will be the g function squared. What is this? This is the x coordinate of multiplication by 2 minus EI. And if you compute that, which I have here, is x squared minus 2EIX minus 2EI squared plus 2E1 plus E2 plus E3 times EI minus E1 E2 plus E1 E3 plus E2 E3, everything squared over 2y squared. And you see it's conveniently a square, so the square root of that is g. Okay, so if you take the squares out, that is actually the definition of your g function. The g function plays little role here, but just so you know it. Okay, now let B1, B2 be in KS2 cross KS2. So what we want, the question here is there a point P, which I'm going to give coordinates already with x, y, in EK modulo 2EK such that BPT1 is B1 and BPT2 is B2. Okay, that is the key question here is is there such a P? All right, so is there such a P? This is if and only if there is X, Y, Z1, Z2 in K cross K cross K cross cross K cross such that it satisfies the Weierstrass equation, and B modulo squares is ft1, and B2 modulo squares is ft2. This doesn't look that bad at all. Now, to simplify, let's put Z3 to be Y is B1, B2, Z1, Z2, Z3. Okay, so define Z3 so that happens. Then what happens? Then if you plug that in into the equations on their left, this is B1, B2, Z1, Z2, Z3. The y coordinate square is x minus E1, but x minus E1 is B1, Z1 squared. X minus E2, that's B2, Z2 squared, and x minus E3. And then if you cancel out terms, what do you get? There's going to be a copy of B1 and B2 left on the left, the Z3 squared, and that is equal x minus E3. So that gives you actually a simpler equation, or simpler to remember anyway, which is B1 Z1 squared equals x minus E1, B2 Z2 squared equals x minus E2, and B1 B2 Z3 squared is x minus E3. But you see, then I can eliminate the coordinate x from this system, and that gives me a system B1 Z1 squared minus B2 Z2 squared equals E2 minus E1, and B1 Z1 squared minus B1 B2 Z3 squared equals E3 minus E1. Okay, so that there's an implication, but it turns out that there is an equivalence. If you find if we find a solution to the system on the right, Z1, Z2, Z3, then you can check that the point xy, which is B1, Z1 squared plus E1, and B1, B2, Z1, Z2, C3, is on the elliptic curve. Okay, so this is in fact a system that we need to solve for each B1, B2, each pair B1, B2. If we solve that, we find a point. And if we have a point, there is a solution to one of these systems. So these are the systems, like we said before, these are the systems B1, B2, which you can see this, it's two equations and three variables. When you cut those, you actually get one curve. And that is, again, what we call a homogeneous space. The homogeneous, you can see that if I made this into projective coordinates, then it's just two quadratic equations. When you actually combine them into one equation, it would be like a quartic, a curve given by a quartic equation. Okay. Oh, by the way, what happens if this didn't work for torsion points, but if P was one of the torsion points, then we can use linearity to compute it, to compute the value of the pairing. the definition of the pairing that, or in the theorem, it did not apply if P was one of the torsion points. So let's compute B of T1, T1. B of T1, T1 would be B of T1, comma, T1 plus T2 over B of T1, T2 by linearity. And this is B1 of T1, T3 over B T1, T2, because T1 plus T2 is the third non-trivial two torsion point. And now I can compute those because now it's not a repetition T1, T1, and those can be computed, and this is E1 minus E3 over E1 minus E2. And similarly for BT2, BT2, the formula is E2 minus E3 over E2 minus E1. Okay, so this is the other values that are useful to compute the Mordelve group. So what we've proved is the following. All in all, we have the following theorem. This theorem is called the complete to descent of elliptic curves, and is the following. So suppose you have an elliptic curve with full to torsion. For EIs in K not equal to each other, let S be infinite places, bad places of E over K, and places dividing M, which is places dividing 2, and let KS2 be classes of K modulo squares such that the order of vanishing at primes is 0 modulo 2 for all places not in S. Then there is an injective homomorphism. Very important that it's injective, so we can actually compute the image. And it's a homomorphism. We're going to be able to exploit the fact that it's a homomorphism once we know something is in the image and something is in the image and the product is in the image. Okay, defined by so an injective homomorphism from EK modulo 2 to KS2 cross KS2 such that PXY goes to X minus E1, X minus E2 if X is not E1 or E2. So P is not one of the two torsion points. It goes to E1 minus E3 over E1 minus E2, comma, E1 minus E2 if X is E1, if P is T1. It goes to E2 minus E1, comma, E2 minus E3 over E2 minus E1 if X is E2, and it goes to 1, 1 if P is O. Okay. And moreover, if B1, B2 is in KS2 squared, if it is in the image, of P not O, T1, or T2, then P satisfies the system B1 Z1 squared minus B2 Z2 squared equals E2 minus E1, and B1 Z1 squared minus B1 B2 Z3 squared E3 minus E1 for some Z1, Z2, Z3 in K cross K, and P is B1 Z1 squared plus E1 comma B1 B2 B1 B2 Z1 Z2 Z3. Okay, so now you see that we have a very strong way of computing the Mordelve group. We have a complete definition of how the E mod 2 maps into KS2 cross KS2, and it also allows me to know what points in KS2 cross KS2 actually come from points on the elliptic curve, or on the Mordelve group, the weak Mordelve group. Remember that if we, given the theory of heights, if I have generators of E mod 2, then I just have to, then it's a finite computation of points with a smaller height to find actual generators for E over K. Okay. All right. So we have a few minutes to start computing with an actual example. Use this theorem to compute with an example. So let me do that. Okay. So here my goal is find all the rational points on an elliptic curve. Okay. My elliptic curve that I'm going to choose is over Q, and it has full two torsion over Q. It's the elliptic curve x cubed minus 12x squared plus 20x. Okay, that factors completely as x times x minus 2 times x minus 10. Great. First step is try to compute the torsion subgroup. Okay, what is the delta of this elliptic curve? What's the discriminant? The discriminant happens to be 409,600, so 409,600. That factors as 2 to the 14 times 5 squared. Let's see what bad primes we have. Well, possibly 2 and 5. 5 for sure is going to be a bad prime. 2 to the 14, maybe this model is not minimal at 2. But Z4 is 2 to the 6 times 3 times 7. So we see that 5 is bad and 2 is bad. If we could have actually, I'm not sure this is enough to prove that 2 is bad in this case, but I'm just gonna tell you that if you try to find a minimal model, this is bad at 2. So there is vector reduction at 2. It is additive at 2. Remember that in the theorem, we're going to have to pick S, the set S. Their bad places are going to be there, but the places dividing 2 are going to be there anyway. So even if 2 was a prime of good reduction, I'm going to have to throw 2 in S anyways. So in any case, I can tell you that 2 is additive in this case, and 5 is also bad, but 5 doesn't divide C4, so the reduction is actually multiplicative in this case. It doesn't matter. Now, what about the torsion? So for the torsion, we certainly have that the 2 torsion is contained in the points defined over Q. Is there more? Is there more to torsion? Well, we can use our tools. Remember, recall that we know that M torsion injects into the points over a reduction when P is good and P does not divide M. So let me do that. So it turns out that for P equals 3, there are precisely 4 points. What does that say? That says, well, 3 is a good prime. Okay, so 3 is a good prime, a prime of good reduction. So all the prime to 3 torsion would embed into this group, but we have, well, the 2 torsion already fills that up, so that's it. So, so there is no other points. So this implies that no prime to 3 torsion other than the 2 torsion. By the way, this also says that, you see, if there was 4 torsion, which I don't know, it would also embed in there. But because there's only 4 points on the elliptic over F3, there's going to be just 2 torsion. There's no 4 torsion either. But what about 3 torsion? You have to do some other prime. P11 is also good. And it turns out that the number of points on the elliptic curve over F11 is 16. So there is no 3 torsion that could embed in here. All right. So the torsion group then has been determined, and it is just the full 2 torsion. No more. All right, great. So now we go for the gold, we go for the Mordelve group. So the Mordelve group says we're going to take S to be the infinity primes. So the prime at infinity. There is the prime 2, because M divides, M is 2. And then other bad primes. So 2 is bad and 5 is bad. So the set S is just infinity, 2, and 5. Then what is the set KS2? In this case, QS2. QS2 will be classes of rational points modulo squares such that the order of vanishing at a prime is 0 mod 2 for primes not in S. So what does that say? That says then that I have, for example, plus or minus 1, satisfy that. But it allows for primes to odd powers. It also allows primes that are in S. So plus or minus 2 can be in here. Plus or minus 5 can be in here. Their products can be in here. So plus or minus 10 can be in here. But that's it. Any other number, any other rational number, which you can assume is an integer, would have a prime factor that that is not in S, and therefore the order of vanishing is 2, therefore there's a square there, and this is it. So actually QS2 is just this. Okay. Notice that it has size 8. Okay. So what does this tell me? Already, without any computations, any further computations, this tells me that the proposition or the theorem of two descent tells me that EQ modulo 2EQ, which, by the way, by the Mordelve theorem, I know it's the torsion modulo 2 times the torsion. Only the 2 torsion survives that. So I get 2 copies of Z mod 2 coming from the quotient of 2 torsion modulo 0, okay, times copies of Z mod 2 to the rank, okay. So this is of size. The size of this is 2 to the R plus 2, where R is the rank, okay? And the theorem of descent tells me that this injects into QS2 cross QS2, which is of size eta squared. But that is 2 to the 3 to the 2, so 2 to the 6. Okay, so this alone tells me that R plus 2 is at most 6, and therefore R is at most 4. Right? So the rank of the elliptic curve is at most 4. And let's leave it there for now. But this is already showing the power of this, that this map already is giving me a bound, a pretty nice bound on the rank. This is saying that the rank is at most 4. And now we're going to use, in the next video, we're going to use all the full power of the map to compute the pairing point pair by pair and reduce this bound until we complete descent and we actually compute the rank exactly, and actually a generator of the weak Mordelve group that gives you the rank. Okay, so I will stop here and continue from here next time.